Well, welcome. Good morning. I'm going to start talking about information retrieval, and please don't hesitate to ask questions as we go along. Otherwise, I'll just drone on and on. So, what is information retrieval? Well, actually, this is the overview. This is what we're going to cover. What is information retrieval? Talk a little bit about evaluation. I think David Urowski in the second lecture will talk more about evaluation, although I haven't seen his slides, so I can't promise that. Then we'll talk about how we characterize documents and queries, how we compare those characterizations, and then a few implementation details. So that's what we'll be doing in this first lecture. All right, so what is information retrieval? Information retrieval is the automatic identifications of documents in some large collection of documents that are relevant to an explicitly stated information need. So to do information retrieval, you have to have some explicit statement of need. And we're all familiar with information retrieval in the context of the web. Google, for example, is a classic example of an information retrieval engine. In information retrieval research, in academic circles, there tend to be some simplifying assumptions that people make. And these assumptions, you will see, are not really applicable to many kinds of search, like web search, for example. But they nonetheless help. They allow researchers to focus on certain aspects of the research and not worry about things, such as the document collection is static. So in many approaches to information retrieval, you assume you have a fixed collection of documents and you're trying to search over those documents. In practice, with something like the web, the collection is not fixed and you have to continually update your index. And there are obviously aspects of the field that look at non-static collections. But by and large, many of the evaluations and so on assume a static collection. There's a general assumption that a document is either relevant to the information need or it's not. There are no gradations. You can't say, well, this document is partially relevant to the information need, or this document is only relevant to the information need if you don't have this document. If you got this one, you don't need this one. So those kinds of things tend to get cast aside. Here's a favorite. There is no user. This is great for people who like to hide in basements and code. Typically, the way research proceeds is you get your static collection. You get a static set of queries. Now, these queries may well have been generated by a real person. But nonetheless, they're a sort of fixed set of queries, and for much of the research, you don't have to worry about trying to interact with the user. And there's a branch of the field that looks at exactly user interactions, but my screen has shut off here. Signal is lost, but you still have it there. Oh, there it is. Okay. I guess I just have to touch this once in a while. Another assumption that people typically make is that all documents have the same form. So you assume that you have this big wad of collections, and they all have probably some simple HTML markup that says, here's the beginning of the document, here's the end of the document, and maybe here's a title. But there's a lot of pre-processing that tends to have to happen in all real cases that when you're doing IR research, you sort of assume, oh, somebody else will take care of that. And I'm just going to get a stack of documents that all look the same. Corollaries to this, all documents are text documents, so we don't have to worry about other things like OCR or speech documents and so on. Also, there's something that this assumption tends to be hidden. People don't tend to think about it, but there's often an assumption that all documents are the same length, that in this static collection, it's all the same kind of document. It's all news stories from Newswire. And so you've all got the same length of document. In the early days, when the machines couldn't handle very large documents, they were all just very simple abstracts. So they were all short. But you you tend to see this assumption throughout much of the research. And then finally, all documents are professionally edited. That is, you don't have to worry about typographical errors or messed up SGML markup or anything like that. So I just lay these out not to say that any of these assumptions are particularly good ones, but just to make you aware that when you're reading through the information retrieval literature, often these assumptions get made. And if you are dealing with if you're trying to figure out an approach to a situation where one of these assumptions doesn't hold, you're going to have to span the gap between the kinds of things you read and the kinds of things you're actually going to have to do. All right, so the goal of information retrieval is to match documents to an explicit statement of information need. So how do we do it? Well, first there's a process of characterizing every document in the collection so that you have some representation for the document other than the stream of Latin 1 characters or whatever it's coming in as. And then because the collections tend to be large relative to the machine's memory, you have to store those characterizations on disk in some efficient way. Then a query comes in. You have to characterize that query as well. And typically you choose the same kind of characterization. So whatever you did to the documents, you're going to do more or less that to the query so that you end up with something that the pieces are relatively comparable. Then for each document in the collection, you run some comparison between your characterization of the query and your characterization of that document. And then typically you return a ranked ordered list of the results. So you say, oh, here, the first result, that's the one I'm most confident is going to be of use to you, and so on, down the list. So those are the basic steps, and we'll step through how those basic steps are accomplished. But first, I'm going to say a little bit about other tasks that often fall under the rubric of information retrieval. And these are things that will typically appear in, say, the SIG-IR conference, which is the premier information retrieval conference. If you think of traditional document retrieval as a fixed collection of documents and a changing set of queries, routing and filtering do the opposite. You have a fixed set of queries and a stream of documents coming by. And as a document comes in, you want to compare it against all the standing queries, possibly directing documents to whoever issued one of those queries if it looks to be relevant. Okay, so that's sort of the opposite take on the static and dynamic pieces. Multimedia retrieval, you want to be able to retrieve images. You want to be able to retrieve spoken data. You want to be able to retrieve written documents. There are branches of IR that do all of those things. Cross-language retrieval, this is actually something that we've done a lot of at APL. The idea here is you have a collection of documents in one or more languages. The queries are in a different language. And you want to find the documents that are relevant to, say, an Arabic document that's relevant to an English query. Okay, why would you want to do that? Well, maybe ultimately you want to translate the document, but you don't want to translate every single document that you have. You only want to translate the ones that seem like they might be relevant to your information need. So if you can identify them first without doing that translation, then you have a big step up, because machine translation is pretty expensive, and human translation is even more expensive. So ultimately, well, I'll let the MT class tell you whether you can rely on the machine translation or whether you have to go to human eventually. Summarization. You'll often find related work in summarization in information retrieval conferences. The idea there is you have some large document or even a collection of documents, and you want to smush it down into a small document or just a simple description of what might be found there. Translation, you'll be getting, I think tomorrow is Machine Translation Day. You'll be learning all about how you can translate from one language to another. For cross-language retrieval, we actually do some translation, but it is of a very different type than you will see tomorrow because you don't have the constraints that the output be syntactically reasonable when you're doing cross-language information retrieval. All you have to do is find the right document. So you can, for example, take a query and translate it to a big mishmash of stuff that nobody could read. But if you can use that as a query against the target language, you're OK, and it doesn't matter that you threw away the syntax. Question answering is often attached to information retrieval research. The idea is instead of finding a document that's relevant to your information need, you actually want to find the answer. So you want to say, where's the Taj Mahal? And get back the answer, oh, it's in Atlantic City or Nevada or wherever it is. Topic detection, where you have a bunch of documents and you're interested in finding new topics that are coming along. So that you have some streaming data and you want to know when something new happens. So there's a lot in common between topic detection and information retrieval because you're matching, in the topic retrieval case, all the topics you've seen already against the new documents. But it can be the same kind of comparison. Classification, you have a fixed set of classes, like a bibliographical hierarchy of some sort, and you want to assign keywords to the documents. So you have a fixed set of classes. You're just trying to bin the documents. Clustering is similar to classification, but you don't know what the classes are a priori. You're trying to induce the classes over this big mass of text that you have. And novelty detection, which I guess I skipped to that from topic detection. I guess technically topic detection is just grouping things by topic, but typically in the evaluations, one of the main tasks they assign is trying to find the new topics. So this is novelty detection. When do you see something new? When is it just old stuff that you've already seen? Okay. So I just give this list to you so you get a sense for the kinds of research that you'll see in, say, the proceedings of SIGIR or SICM or some other information retrieval conference. And these touch on a lot of other human language technologies. But these are the ones that have sort of been in the forefront of the field for a while. Okay. I'm going to say a few words about evaluation. I'm not going to go into it in detail. Like many human language technologies, you'd like to know, if you develop a system or an algorithm, you'd like to know whether it works well or not. So you'd primarily like to be able to compare the results of one system against the results of another system to figure out which one is doing better. So how do you do that? You need at least two things. You need an answer key, something that says, oh, for this stated information need, here are the good answers and here are the bad answers. This is where the black and white relevance assignments come in. In information retrieval, it's typically assumed that a document is either relevant or it's not. Okay, that makes having an answer key very easy, because for an answer key, all you have to do is tag each relevant document in the collection, and you're done. Now, that can be a very expensive process. You may have to sit a person down and actually read those documents, and that can be painful. But it does make the basic mechanics of the task pretty straightforward. So you need an answer key, and then you need a way to score a given set of retrieval results based on that answer key. So here is how much of straight document retrieval is scored. Remember, we assume a document is either relevant or it's not. So here we have all the documents in the collection. When you give an information need, the system will retrieve a set of documents. Okay? Now let's imagine at first that we don't have a ranked list, that all we get back is just a set of documents, and the system says these are relevant. Okay? If that's all you get, then this didn't go on, and my immediate inclination was to look at it and turn it on. I said, no, don't do that. Maybe the battery's dying. So you get back a set of retrieved documents and a set that you didn't retrieve. Okay. Now, from those documents, there's also some that are relevant to the information need. Let me switch to this thing here. See if this works. Oh, you can sort of see it. There are, I'm sorry? All right, why don't I use the stick? Well, this is like this yardstick, you mean? Okay, it's even got a little white tape there. We've said that documents are either relevant or they're not relevant. Okay, and this is just for one query. Okay, we've got one query in mind. So for that one query, this set of documents are relevant. This set of documents are not relevant. Okay, these are the documents you retrieved. These are the ones you didn't. Okay, so in information retrieval, you typically use two measures called precision and recall. Precision says, of the documents that you retrieved, what percentage of them were actually relevant? Okay, so precision is, of all these ones that were retrieved, how many were relevant? Okay, so you want this piece to be as big a piece of all the things you returned as possible. Okay, so that's precision. It's the relevant retrieved divided by all the retrieved ones, the percentage of the ones that you returned that were actually good. Recall is how many of the good ones did you actually return? Remember, we didn't return all the documents. We just returned some of them. So we got some of the relevant ones, but we missed others. Okay? So recall is, out of all the ones that are relevant, how many did we get? Okay. And so that's the recall measure. And most information retrieval evaluations use precision recall in some way. Now, it turns out that it is very easy to score very well in these measures. For example, you can go out and in 5 minutes write an information retrieval system that gets 100% recall. You just return all the documents. Say, here they are, here's the whole collection, I've given you everything relevant. Okay? Now, conversely, you can't necessarily guarantee that you'll get 100% precision, but you can come pretty close if you just return very, very few documents. If you pick the one document that you're most sure of and just return that, if you have a decent system, you can probably hit a relevant document most of the time. So you're getting huge precision, but your recall is very low. Okay? So it doesn't make sense to talk about these measures independently. And you will see, if you look through the literature, people talking about this is a precision technique or this is a recall technique. Okay? Don't buy it. You can't talk about one without talking about the other. Okay? Now, this assumes that you have just one query and you just return one set of documents. Okay? However, most retrieval systems these days don't just return one set of documents. That's what they used to do. Back in the 60s, you'd put in your query and you'd just say, here are all the documents in some order. So you would want to, depending on how many you got back, you might throw away terms or add terms to try to control the size of the set you got back. Now we typically get ranked results, but we still use these same measures, and here's how. We build a graph that looks down through the results. So we've got a ranked list of results. And you just start moving down through that list. And at each point, you calculate your precision. Okay? So here in this graph, recall is along the bottom. This is going in this direction is looking deeper and deeper and deeper into your results. Okay? As you look deeper into your results, typically you will see fewer and fewer relevant documents. Okay? So if the information need is pretty clear and it matches the collection, then your very early results will have high precision. But as you go, the precision will drop off. So typically, people for ranked retrieval will use this kind of precision recall curve. Okay, and it's sort of like a rock curve, but you got to turn it and bend it, and but it's sort of the same idea as a rock curve. However, people are lazy and they don't like throwing these graphs around. People still just want one number to characterize their system. So the most common number that people use is called average precision. And that's effectively just the area under this curve. Okay. So you'll see average precision in evaluation results. Now, if you just do this for one query, you don't get a lot of information because the variance is pretty high. So typically, you average over many queries. Often that number is about 50 in information retrieval evaluations. And so the area under the curve averaged over 50 or so queries is usually called mean average precision, MAP, M-A-P. Okay, so when you see that, you know they're just talking about this curve, the area under it averaged over many queries. Okay. Now, doing that really hides a lot of information. It hides in a couple ways. If you just look at the area, you sort of don't know the shape. And very often, for many applications, what you care about is this low recall, the very few first entries in the list. So the mean average precision kind of covers that up. You don't know exactly where you're hitting here. Some applications you really care about having high recall, getting all the relevant documents, and so it's a little better for that. The second way it hides it is averaging over many queries. These queries look all over the map. The best possible performance is a straight line across the top. Right? That says that as you look deeper and deeper into your results, you're getting all and only the relevant documents. And but the actual curves go all over the place. Here are some actual curves. These are actual precision recall curves from an evaluation called TREC 8. TREC is the Text Retrieval Conference. It's the main evaluation in this country for information retrieval. There are others around the world. There's CLAY in Europe. There's NT-SIRE in Japan. Now there's FIRE in India. They all use sort of roughly this methodology. And so these are curves from TREC 8, which was, who knows, a decade ago or so. I don't know what they're up to now, but this is a long time ago. But this is just to give you a sense for what the curves actually look like. Now, these are average curves, so these are average over many queries. And what we have here are so the way these evaluations work, I should say, is NIST runs an evaluation. They get a big wad of text. They give it to whoever wants to play. You take the text, you index it. NIST then gives you a set of, say, 50 information needs. You run them through your system. You send back to NIST your ranked lists of results. Then NIST hires retired intelligence analysts to sit down and look at the document and say, yeah, that's relevant. No, that's not. Yeah, that is. Okay. Now, actually, what they do is they get those same analysts to pose the questions. So you actually sort of have a notion of a user who has a real information need, and they try to get the same person to judge it as made up the question. But and so this is the result of such a thing. This blue line here is the median system at that evaluation. Okay, so you can see if this is perfect performance, systems are nowhere near it. Okay, This line is the top system that year. Okay, so you can see there's a lot of area under here. There's a big difference between the two systems in terms of mean average precision. Okay, but still, the top system was near the top. Okay, now that's maybe not so bad because this line is the best human-aided system. Okay, so in this one, a person got to sit down and look at the type in the query, look at the diagram, say, yeah, that one's relevant, no, that one's not. Okay, so even the top human system was nowhere near the theoretical best. Okay, so it's a hard task for a variety of reasons. One of them is that inter-assessor agreement is not always that high. That means that if you take two assessors and ask them both, is this document relevant to this information need? One will say yes and one will say no. Okay, you can look through the judgments for these things. There's some duplicates in the collection. There'll be a duplicate in the collection. One will be judged relevant, one will be judged non-relevant. So even within a single assessor, it's from time to time, it's not necessarily accurate. So for those reasons, you don't get a straight line across the top. But you can see that, at least as of this evaluation, there was a big difference between automatic and manual performance.
The person or people who did the top manual run, were they using the top automatic system? Or, for example, is it possible that another system found a document that they would have judged relevant, but their aid or tool never found it?
That is possible. I don't remember at this point who that system was. But they do look at how many documents are uniquely found by a given system. And the manual systems are far ahead of any of the automated systems. The automated systems, you know, they all tend to use the same techniques because you read the papers from last year and you implement what they did. There's in all these evaluations, information retrieval or anything else, there's a lot of good science that's promoted by it, but there's also a lot of games and shit that just goes into trying to pump your score up. Okay, I'll give you an example of that in a minute. Anyway, this is how these things are evaluated. Okay, so that's all I'm going to say about evaluation for now. Let's talk about how we actually characterize documents and queries. So we're going to use the same technique to characterize documents and queries. Yeah.
Can I just ask one question about the he said, so do they just have one, when they do the relevance when they do the answer key for the evaluation, they just have one person do it, or do they ever have two people or three people do the same one and sort of take the best, like use voting, or is it that's too expensive?
There have been inter-assessor agreement studies where they had more than one person doing the judgments, but that's not the standard. The standard is you have a single person posing the query and making the judgments. Okay, so whatever that person had in their head about what they were looking for, that's ground truth. And if they say this document is relevant, it's relevant. Okay, so there's in some ways it's unsatisfying, but in some ways it's very satisfying because it's very realistic that you don't necessarily get a lot of information about that user. You only get what they say they want, and then they get to decide whether what you returned was what they really wanted. Okay, so that's in some senses a very realistic task. That's why they typically make sure that the same person makes up the query as does the judgments. All right, so we want to characterize documents and queries. How are we going to do that? Well, first we're going to chop the query up into pieces in some way. We'll fiddle around with them to produce what we'll call terms, or indexing terms. And these are the fundamental pieces for information retrieval. Much as a word or a lemma might be a fundamental piece in some other kind of system. Then typically we take all the terms in the document and throw them into a bag. Okay, we dump all of the ordering information. We assume that they're all independent, and those are gross simplifications that we make. But with some good reason, because it turns out this works pretty well, and trying to do anything else doesn't always seem to work. This is often called a bag of words approach. Okay, chop the text into words, throw them in a bag. That's your representation. Okay, you can also get terms from outside the text, so you don't have to just chop up the text itself. There's metadata. You might know who the author is, or the Library of Congress catalog number, or something like that, or categories. You can do references. So, for example, if you either incoming, you can take incoming links or outgoing links. You can use text associated with those references. So this is a very common thing in web search, for example. You'll go to a web search engine and you'll type in a query and you'll get back a document. It'll say it doesn't have one of your query terms. Where did that query? Why did they return this document if it didn't have your query term? It's because another document that did have that query term had it as part of the link pointing to this page. Okay, so you can get terms from other places, but typically they just come from the content of the document. Okay. So by far, the most common kind of indexing term that people use is words. So that means in something like English that you do something like break at white space, so chop everything up at the white space, throw away the white space. And so if our text is 4score and 7, we might chop it up into 4score and 7. Often we'll downcase all the words so we can avoid problems with the beginning of a sentence not matching the query term the person puts in. A couple of very common operations are called stopping and stemming. Stopping is throwing away words from the document or from the query. Think about your favorite query. You want to find out about the purple dog, and you type in the purple dog. Well, the word "the" in that query probably occurs in 90% of the English documents that are out there. Okay? So what is the discriminative power of "the"? It's very low. Okay? On the other hand, what is the processing cost of "the"? It's very high. And you say, well, let's find all the documents that have "the" in it. Okay? So you grab the whole web, English web, and there you go. So for that reason, systems will often just throw away words. Okay? So here, 4score and 7, and is a typical stop word. We'll just throw it away. And if systems will typically have between 10 and 100 stop words that they'll use, and they'll just throw them away. There is no, you're not gaining any quality by doing that. Sometimes people think, oh, stopping is, I better put stopping in my system to improve the quality. You're not getting better quality because any decent measure is going to realize that something like "the" is very common and downweight it. But you are presumably getting a performance benefit. Stemming is another operation. Stemming is poor man's lemmatization. It's simply finding some root of the word, most often in Western languages, by chopping off suffixes. Okay, so 4score and 7, instead of years, you'll put year. That way, anything that has year or years will match. Okay, so those are two very common kinds of operations that tend to get applied to the words. You have to do this language dependently because the operations you do on a given language are going to be very different. Okay, so if you take a system that does stemming for English, try to apply it to another language, it's not going to work. The rules for what suffixes are good to drop are different for English than for other languages. So if you're doing word-based retrieval, you really have to be language specific. And if you're going to go to a new language, you need new stuff. There are also problems with word-based systems when you have data that's not pristine. So if you have OCR data or something like that, you have problems because if you get a mistake in an error in a word, that word is no longer useful as an indexing term. I'll talk quickly about one alternative that you will see used, especially in Asian languages, where you don't have obvious word breaks. So typically in Chinese, you don't have spaces between the words, so you have to figure out where the word boundaries are. That means that for Chinese, you have to have a Chinese-specific segmenter that will try to find the word boundaries. Character engrams are an alternative to words that are useful in a variety of situations. For those of you with any speech background, if you hear about engrams, you'll be thinking about word engrams, sequences of n words in a row. That's not what we're talking about here. We're talking about character engrams, sequences of n characters in a row. Okay, so if our text is 4^7 and we're doing 5 grams, the first 5 gram is FOUR blank, the second one is OUR blank S, and so on. Okay. Now, this may seem kind of wacky. What's the semantic content of UR blank SC? It's perhaps very low. Okay, but like the First Change Bank, if you've ever seen that fake commercial, 5 grams get some power out of this in among other ways through volume. That is, when you have words, only a few of the characters begin a word. Every single character begins an n-gram. So if you're doing n-gram-based processing, you actually have many more indexing terms. So if the semantic content of each one is lower, it doesn't matter because you have more of them. N-grams are very good for doing cross-language work or for applying information retrieval to a new language. I already mentioned the problem of word segmentation in Chinese. N-grams don't care. You just take Chinese characters in a row. Typically for Chinese, if you get only one N, pick 2. If you get more than one N, pick 1 through 3. You get very good retrieval results without doing any word segmentation. There's a sort of the opposite problem, or a similar problem in languages like German, like agglutinative languages, where it's perfectly legal to take 2 words, glom them together, form a new word. Never been seen before, will never be seen since. It's a legal German word. So in German, information retrieval systems that are word-based struggle to break these things apart so that you can use the individual pieces. N-grams don't care, they just march over it. If you have an error in a word, that word is useless in a word-based system. In an n-gram system, the n-gram before the error and the n-gram after the error are both fine, as are all the other ones. I've seen studies where people have degraded text, take a collection, and duplicate the collection with 5% errors, 10% errors, 20% errors, 30% errors. And then you do an n-gram system and you do retrieval against it, and you say you're doing no item retrieval, where there's a particular document you're looking for. You type in a query. The first document back is the undegraded document. The second one is the 5%. The third one is the 10%. And it goes down to 20 and 30%. You can't read this stuff when it's up there. It looks like gobbledygook, and an n-gram system will nail it. So there are a variety of reasons that you might want to look at an alternative like character n-grams for your indexing terms. They are disadvantageous for a number of reasons. Larger posting files, we'll talk about that in a minute, basically means the data structures you need to handle them are bigger. And they don't mesh well with natural language processing techniques if information retrieval is only one piece of your processing pipeline. Okay. And largely for this reason, they aren't used by the big web search engines, but because it's a little bit slower to do, and they're so concerned with speed. But if you're doing multilingual work, it's quite a reasonable choice in information retrieval. Here are some examples of precision recall curves in various languages. These are from our haircut system, the Hopkins automated information retriever for combing unstructured text, which was this system we had that that does retrieval in many languages. These are monolingual retrieval results showing both words and n-grams. And you can see for English, words and n-grams perform largely the same. For many languages, they perform largely the same. Here's German. Look at this huge difference. This is n-grams, this is words. Why is that? Because with n-grams, you're getting the automatic decompounding. If you just use straight words, you're losing a lot of indexing terms from the compounding. So here, so if you just use n-grams, you get that for free. So it's a reasonable approach. Once you have figured out what these pieces that you're going to use as indexing terms are, you might want to weight them. Okay, so you might want to treat some as more valuable than others. Why would you want to do that? Well, we've already talked about the case of stop words. The is so frequent that its discriminatory power is very low, and so if you didn't stop it, if you were actually using it, you would still want to downweight it. Okay? Even a word that isn't a stop word, like maybe company. Maybe company is not a stop word, but it's think about company and sprocket. Okay, so if you have some query that has company in it, well, you know, company is probably important, but it's a common word, and sprocket, that's a very specific word, and you probably want to make sure to match that. Okay, so so we use we think about two different ways of weighting a term. You want to weight a term more if it occurs more frequently in the document of the query, right? So if you have a document over here that talks about sprocket 17 times, and this document talks about sprocket once, well, you know, sprocket is probably a more important term in the document than 17. So you'd like to increase its weight according to the term frequency within the document. By the same token, if you look at across all the documents, if most of the documents have the word company, even if the document has company a lot, you say, well, we don't really care. We're going to downweight that. So you'd like to have a term frequency component that gives higher weight if a term occurs more frequently in the document. But if you think about this notion of document frequency, what percentage of the documents does the term appear in? You sort of want the weight to go with the inverse of the document frequency. A term that appears more documents should be downweighted. So we call it inverse document frequency. So you'll see reference to TF-IDF. TF-IDF means term frequency, inverse document frequency. So you want to weight terms higher if the term frequency is high, but lower if the document frequency is high. And so this is a classic TF-IDF weighting function. You have some word, you've chopped your document into words, you have this word, you want to try to give it a weight. So you say, well, how often does it appear in the word? Term frequency. How often does it appear in the collection? This is the total number of documents in the collection. This is the number of documents containing the word. So we take the inverse of that and we throw a log in it because we do. And this is a classic weighting function. Okay? Now sometimes you will hear people talk about TF-IDF as a way of comparing two documents. Or comparing a query to a document. Okay? It's not a comparison function. People will say that, but they don't mean that. They mean a comparison function that uses TF-IDF. TF-IDF is just a way to weight the terms. Okay. So, so we've got our document and our query. We've chopped them up into pieces. We've assigned weights to each of those pieces. So now effectively we have a vector for each document, a vector of terms with their weights, and a vector for our query, a vector of terms with weights. And now we need to compare those two vectors to see whether they're close. There are basically four main models that are used. There are other models. There are a lot of comparison models, but these are the four most commonly used. Boolean vector probabilistic and language model. Let's start with Boolean. And then there are a couple other topics I'm going to talk about: hybrid retrieval and blind relevance feedback. Let's start with the Boolean model. The Boolean model was one of the earliest information retrieval models, and it basically said make the query be a Boolean combination of terms, and the documents you return are all those documents that satisfy that Boolean combination. So here's an example. Wild and either cats or jaguars, and not football. Okay, and or not, classic Boolean operators. This would, in an old style system, your queries would look like that. And consequently, ordinary people probably couldn't put together good queries. So you needed trained librarians to be able to put together a good Boolean query. And they did a great job, but it took a lot of training. And this would, the comparison operator is basically find all documents that satisfy this query. So if you had the Jaguars had a wild card berth in the National Football League, you would not return that document because while you match wild and you match Jaguars, it said not football, you had football, so you don't return that document. Okay. So this is probably the earliest widely used retrieval mechanism or comparison mechanism. The straight Boolean model does not allow for ranked results. So you don't get back a ranked list of documents. You just get back a blob of documents. Here are all the documents that match that Boolean query. Okay. So there are extended Boolean models that add things like proximity operators. Wild near cats. So the two terms have to be close to each other in the document. Or wildcards, match anything, star J, yeah.
How come they don't rank the results if they do that? Or is there some reason, so they get back all the documents that are relevant to that, but then couldn't they still?
Well, yeah, so these extended Boolean models do rank, okay? So, yeah, you're just getting a little ahead of me. With an extended Boolean model, you add a ranking mechanism over the Boolean operator. So you would have some way of saying how important these different terms were, and then that importance would get mapped onto the document. So you'd have some combination of those importances. You get a score back. You could rank them based on that. Okay. So extended Boolean models have that. You've probably seen these pseudo Boolean operators, plus and minus. For example, Google allows you to do that to say, well, you don't have to say plus because Google defaults to this term must be in the document. That wasn't always the case. From very early on, the default in any information retrieval system was or. So either this term or that term or the other term. It might try to weight a document that had both terms higher, but the default was or. Google was the first one I knew about that defaulted to and, so that the term must be there or you don't get the document back. And they were able to do that because the web is so large that you don't have to worry about not getting any results back. It drives people crazy if they put in a query and they don't get results back, but you don't have to worry about that now. So, default and allows you to have effectively shorter queries that still get good results. So you don't really need the plus, but you can do minus in front of a Google term. Say, make sure this term isn't there. That's not. It's not full Boolean retrieval, but it does sort of. It allows you to do partial Boolean expressions. So in a basic Boolean model, they thought of precision and recall as sort of being separate in the following way. If you're not returning ranked results, if you're just getting back a big blob of documents, then something like stemming, where you take a word, chop off the end so that juggle matches juggler matches juggles, that is in effect a a recall enhancing technique, right? If you do that, you're going to get back more documents, because if your query says jugglers and the document says juggler, if you don't do something like stemming in a Boolean system, you won't get back that document. If you add stemming, you now get back that document. So the set of documents you get back is larger. So people thought of that, oh, that's a recall enhancing technique. And maybe it was completely orthogonal to what kind of precision you were getting out of the query. Okay? So in a Boolean system, it sort of makes sense to talk about a technique that increases recall independently of the precision. But since in a rank system, you're effectively getting back all the documents, just the ordering that matters. So you will see this kind of language getting carried over into recent documents, and even today you'll see papers. This is a recall technique. Okay, well, it's not. It's a technique that maybe sets you at a different point in the precision recall curve or whatever, but you really can't talk about them independently. Second model. This is probably the most widely cited model, the vector-based retrieval. Remember I said that we effectively have vectors. We have a document is characterized as a set of terms and a weight for each of those terms. Okay, so you can think of each one of those terms as a dimension in a high-dimensional vector space. Okay, so if you have the purple frog, the document the purple frog is going to be, if that's the text of the document is the purple frog, then that'll be extent 1 in the direction, extent 1 in purple direction, extent 1 in frog direction. Okay, the green frog is going to be 1 in the, 1 in green, which is another axis and frog. Okay, so we can imagine documents being spread about in this high-dimensional vector space. And we can imagine a query being a point in that space too. So now we have a document that's, I forget how I was doing this, but let's say here's a document and here's the query. Okay. We can say, well, how close are these? Documents that are close to the query in this space are going to be better than documents that are far away. Okay. Now, we probably don't just want to use Euclidean distance, because a document, if you just take the purple frog and duplicate it 100 million times, and that's your document, that's a pretty good match to the purple frog, but the distance is going to be very hard because of the... So what people typically do is not measure this distance, but measure this angle. Okay, and since so here's from the origin. There's the vectors of the document. There's the vector of the query. You know, maybe the query is down here because it's shorter. Okay, but we measure the angle, and we like to have a measure that goes from 1 for very relevant down to 0 for not at all relevant. So we take the cosine, and that's exactly what we have. Cosine goes to 1 when you have the same vector, goes to 0 when they're completely orthogonal. So you can have the space use the cosine, and the cosine is simply the normalized dot product. So all you really have to do is take the dot product of the query, the vector for the query against the vector for each of the documents. Okay, and then there's a normalization factor. And that's your similarity metric. Okay, so if you hear somebody talking about a TF-IDF system, chances are what they mean is a vector-based system using cosine similarity that weights the terms with TF-IDF. Okay, so that's what you're hearing. There are things you can do to spice this up. You can use latent semantic indexing. It's basically a principal components analysis of the vector space to transform it to a new space that's lower dimension, and that moves dimensions that are semantically similar together. So car and automobile, if you do this kind of decomposition, might end up being on the same axis or close to each other. So you can manipulate the space. There are other ways to measure the distance between two things. You know, if you have a centroid, you can measure the angle there. There's a bunch of things you can do. But typically, this model is TF-IDF weighting, characterize things by vectors, measure the cosine of the vector between the query vector and the document vector. Okay. So that's probably the most famous model. There are a couple others that have gained a lot of currency recently. The third one is probabilistic retrieval. And probabilistic retrieval is, in some ways, it's just a grab bag of a bunch of different techniques that people put together. It comes from what's called the probability ranking principle, which says that you get optimal performance in retrieval if you rank the documents according to the probability of being judged relevant. So if you can assign probability to the relevance of documents, then the probability ranking principle says rank them in that order. It sort of makes sense, but that had to be articulated at some point. And often you'll see odds used rather than direct probabilities. Often what these probabilistic methods boil down to is different term weightings. Okay? And in fact, the most famous is Okapi BM25. So Okapi is a system developed, I guess, by Steve Robertson and others. And they just tried a huge slew of different weightings. And one interesting thing they did was that they factored document length into the weighting. This is not, remember I talked about the assumption that all documents are the same length? Well, recently we're getting very large collections and there's a much greater range of document lengths in these things. And that led to some of these similarity metrics not working very well. So they actually, BM25 actually has a document length over average document length component to it. Okay. So if you hear about probabilistic retrieval, they're probably talking about this principle and Okapi BM25, probably, or this class of things, but it's basically term weighting. The last similarity metric I'm going to talk about is called language modeling. And for those of you who have some speech background, this will look somewhat familiar. Basically, we're treating a query as a statement in some language. Okay? And we ask the question, if we had a language model that could spit out arbitrary sentences, what's the probability that that model would spit out this query? Okay? And we do that for each document. So we take a document and we say, let's imagine that this document is a language model. That is, and a language model is just something that spits out sequences of terms. Okay? Let's imagine that this document is a language model. What's the probability that that language model would generate this query? And we ask that question for every document in the collection. That gives us a probability for each document. We rank according to those probabilities. That's the basics of a language model approach to IR. So here's an example. We have this is a language model. In this language model, every time you emit a word, 10% of the time it's the, 20% of the time it's purple, 20% of the time it's green, 50% of the time it's frog. Okay? So if we have the purple frog, the probability of generating the purple frog from this language model would be 10% times 20% times 50%, and somebody who's cleverer than I can multiply that out. But it's some probability. Okay? So we want to generate one of these language models for each document in the collection. Okay? Now, we make a very strong simplifying assumption that all terms are independent. Okay? In terms of language models, we're basically using a unigram language model. That is, we're outputting a word, and then no matter what that word was, the probability for the next word is going to be the same as if the first word were a different word. Okay? So these probabilities are all independent. And the way we we turn a document into a language model is we say, okay, well, this document is simply going to emit terms according to the frequency with which they occur in that document. Okay, so if I had a document that had the purple, purple, green, green, frog, 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 then this would be our language model, right? Because half the words are frog, 20% are purple, 20% are green, and 10% are the. Okay, so if that's our document, we have a language model, and this is how we score it. We say the probability of a query given that document is simply the product of the probabilities of generating each one of the terms in the query. Okay, so if our query is purple frog, then 20% times 50% is 10%, I guess. So that would be our score. And we simply use the maximum likelihood estimate to get those probabilities. Maximum likelihood estimate is simply just the percentage of the number of occurrences of a word in the document divided by the total number of words in the document. Okay, so it's very simple. Now, this model itself is a little bit broken because we're multiplying probabilities. What if we have a query? What if the query is a purple frog? And this is our document language model. Okay, well, we get purple frog 20% times frog 50% times a 0%. Okay, 0 gone. That document is not relevant. Well, it has purple frog. It probably ought to be a decent match. But the fact that our query had the word a and the document did not turn this probability to 0. So we have to do smoothing, and this is again, for those of you in the speech world, this is second nature. But basically, smoothing says we need to give credit for the word a, even if it's not in the document. Why? Because a is a common word. Okay, so the way we tend to do that is we say, okay, well, let's take a big collection of text, and and we will take some of the probability for generating a from the document itself, and some from the big collection. There's a big background collection. So we have some number alpha between 0 and 1, and we say part of the time, for part of the weight, we'll take it from the document. For the rest of the weight, 1 minus alpha, we'll take the probability of the query given the collection as a whole. What's the likelihood of this term being generated from the collection as a whole? And so this is a standard unigram language model for information retrieval. And it's one of these things that basically was independently invented by a number of different people with using different language. So one set of people talked about language models, one set of people talked about hidden Markov models, and so on. And they all came up at the same time. It was, so this similarity metric doesn't need TF-IDF weighting. Okay, we don't weight the terms with anything other than what you see here, and that's because you get the term frequency from the document itself because you're looking at if a term appears more frequently in the document, this probability is higher. Right? You get the inverse document frequency from this smoothing. So if a word like the appears very frequently in the collection, then this piece, the probability of that query term given the collection as a whole, this is going to be pretty high. And it's going to be pretty high for every document. So that's sort of going to wash out the fact that you get a match in any particular term. You're looking at the whole collection, and that's where you get the IDF piece. So we don't have to explicitly TF-IDF weight terms in this language model. All right, I guess I have about 5 or 10 minutes left. So I'm going to skip that. It's going to signal is lost. I think I'll skip that. I do want to talk about blind relevance feedback. This is a technique that is used pervasively in information retrieval research because it gives a big boost to scores. The basic idea is that when people give a query, they don't give all the good terms that might be useful for that query. They only give some of them. So if I want to find out about cars, I might type in car. I didn't type automobile. Now, if I type in car, and I'll get back some documents, I might look and say, oh, this document is relevant and this document is relevant. I really like those two. And then the system can say, oh, okay, I'll take those relevant documents, pull terms out of those, add them back into the query, and get a better query. Okay? So that's called relevance feedback. You're taking judgments by the user, taking the documents that come from those judgments, pulling terms out of them, adding them back into the query. Okay? That's relevance feedback. Blind relevance feedback says, we don't need no stinking user. One of our favorite simplifying assumptions. In blind relevance feedback, you take your retrieval results, say, oh, I probably did a pretty good job of retrieving these. I bet the top n documents are relevant. So I'll take those documents, pull terms out of them, add them back into the query. And if you do that, you almost always get a boost in mean average precision. So here's a typical example without blind relevance feedback, with blind relevance feedback. Okay. Now, this is important for a number of reasons. One, it's a widely used technique when you don't have to worry about speed, which means not the web. But it's widely used because it gives you this huge boost in mean average precision. That may not look like much, but that's a huge boost in mean average precision. It's also important because it's misleading. And it's misleading because we're looking at mean average precision here. We're not looking at individual documents and queries. We're looking in aggregate over many. And what you'll find if you tease this apart, if you look over all the documents, what blind relevance feedback typically does is takes the queries you're doing well on and makes you do really well on them. And it takes the queries you're not doing so well on and drives them into the ground. And since you weren't doing well on them anyway, you're not losing much. And the ones you were doing well on, you can get a big boost. Okay? So that's where this is coming from. And so you'll see in information retrieval evaluations, people will tend to use blind relevance feedback, depending on the task, but it's pretty common for basic ad hoc retrieval tasks. And yet it's not necessarily doing what you want, and you really have to tease apart the individual queries and take a look under the hood to decide whether it's really something you want for your application or not. Okay. We have time to talk about implementation. Yeah, I mean, since I think you're going to be actually doing this later, so I'll continue on with implementation. So basically, we took documents, we chopped them up into terms, we weighted those terms, we came up with a way to do similarity comparison. So we have a representation of a document, representation of a query. We take a similarity, we get a score, and we rank our results according to that score. Okay, so that's the basic flow of ad hoc information retrieval. To actually do this, you need to be a little bit clever about how you index things, because you're dealing with lots and lots of documents, and you have to be able to basically find all the documents with a given term. And the principal data structure used to do this is called an inverted index. Why it's called an inverted index and not just an index, I don't know. But basically an inverted index has a dictionary. So it has a dictionary of all your terms. And typically you'll hold that dictionary in memory. Okay, so you load the whole index into memory. And if you look back through the literature in the early days, people were always trying to figure out how to keep the dictionary in memory, because just keep all the words that possible in memory, because the memory was so small. And there's all kinds of great schemes for compressing these dictionaries. For each term, you want to know which documents contain that term, And the file that says which documents contain the term and how many times it occurs in that document is called the postings file. So this is the index, this is the postings. And if you think about what you have to start with, you have a document, you have a set of documents, and you know the document name, and you can easily map from the name of a document to all the terms in that document. And you want to sort of flip that around so you can easily map from a term to all the documents containing that term. Okay, so that's where the inverted comes from. You're sort of inverting the mapping that comes into the system. So we started with doc42 that had alfalfa in it. And now we want to be able to say, oh, alfalfa, that's in document 42. There are other data structures that people use for this, but the inverted index is the most common. David, do you know if are they actually going to be building an inverted index? Okay, so you're going to build one of these things. So you're going to have to take a set of documents and invert it so that you can map from terms to documents. So you'll have a dictionary. That's a list of all the terms in all the documents. And you'll probably keep that in memory. And the postings, this is typically kept on disk. So that you need one seek for each term in the query. Okay, so that's why longer queries take longer because you have to do a seek for each term. And that might be all I have on implementation here. Yeah, so let me just summarize what we've learned. Information retrieval is the automatic identification of documents that are relevant to an explicitly stated information need. So you have some explicit statement of need, and you're trying to match to that. There are a lot of different problems that, related problems that often go under the rubric of information retrieval and appear in the information retrieval evaluations and the conferences. We talked about those. Precision and recall are the most commonly used metrics for information retrieval, and they tend to get boiled down to average precision if you have a ranked set of documents, and then averaging those over many queries to get mean average precision. The way that people characterize documents and queries is typically by some variant of words, usually somehow manipulated by stemming, for example, to get closer to a lemma for the word. Once you characterize these, you weight them, and then you need a similarity metric. And there are four main similarity metrics that have been used: Boolean, the vector model, probabilistic model, and language model. And there are techniques to improve performance, but you have to be careful and look under the hood to see if it's improving the performance in the way that you want. And because the collections are large, you have to be very careful about the data structures you use to actually implement it. And then inverted indexes is a typical way to do that, which you will do this afternoon. So that's all I have. Are there any questions? We're going to have, I should just say, we're going to have David Urowski in the back here is going to give a second lecture. And then this afternoon you'll have a practicum where you actually get to implement one of these things. Questions?
Is the inverted index still useful for the n-gram model?
Is the inverted index still useful for the n-gram model? Yes, absolutely. N-grams are simply one kind of indexing term. So you still need a way to map from a term to the documents containing that term. So, sometimes you'll read about n-grams being some strange beast unrelated to words. They're not. They're just indexing terms. Okay, and so if you have an indexing term, you have to have a way to map from that indexing term to the documents containing that term. And an inverted index is a good way to do that.
Do these n-grams create a lot of false positives?
Do n-grams create a lot of false positives? The answer is yes, in that it's certainly possible to have a common n-gram that matches a lot of things that you didn't want to match. Okay, but in practice that doesn't hurt you, because in practice A, it's the rare n-grams that are giving you more of your score, because the common n-grams will have the same thing that happens with common words will happen to common n-grams. If you say you're using the language model, okay, the common n-grams will be common in the collection as a whole, and so they'll get counted across all the documents, and they won't boost the score that much. Secondly, you have many more n-grams, and so if you think about a phrase like 4 score and 7, maybe each of those n-grams might be fairly common, but how many documents are going to have all of those n-grams? Probably very few. So the ones that actually match 4 score and 7 are going to go right to the top.
And how are terms different from words? I mean, in the indexes, for example, do you have like multi-word terms?
Oh, okay. Yeah, that's a good question. Do you have multi-word terms in an index? It is certainly possible to treat phrases as individual terms and throw them in your index. So to do that, you would need to identify the phrase, and then you'd probably put in the phrase and the underlying words itself into the index. That's not typically how it gets done if you're trying to do phrases. Typically, what they'll do is they will add some information to the index that allows them to reconstruct the word order. So one way to do that is in your, if you go to your postings list, in addition to saying document 42 contains 3 occurrences of alfalfa, you can say, oh, and those happen at positions 2, 19, and 48. Okay, so that's one way to do it. That's not the most efficient. There's what's called a next word index that basically lists the words that can come after a word. And I no longer remember the details of how that works right now, but it's a reasonably efficient way to be able to recreate the sequences of terms that are in a document without actually indexing the entire sequence itself. And so that's typically how it's done. That's probably where the web search engines work. I haven't said anything at all really about the web search engines and what goes on with them. In part because a lot of it is secret. So you might know all the relevant people at Google, but you're not going to get them to tell you how they do it. They have been reasonably good about talking about things like PageRank, which is a component of their algorithm. And PageRank basically... Okay, so very good. So you will find out all about PageRank. So you should get a little more from David about that. So I won't say any more. Other questions? Yeah?
Do they ever tell you what their score, like their mean average precision score is?
Something like Google?
Yeah, so that you could compare it to what?
Will Google reveal how well they do on an evaluation task? Almost never. There is an occasional corporate interest that will do something like that. For example, Microsoft researchers have traditionally submitted systems to the Trek evaluation. So the whole Okapi BM25, that was developed as a way to try to do better at this Trek evaluation, and they published it. But that is not the same as their commercial engine. So certainly they're using pieces of it in their commercial engine, but they're not going to tell you which ones. You can try to figure it out. If you by judicious entry of queries, you can and timing how long it takes to do things, you can figure some things out. But no, they're not going to tell you. Okay, well I think we have a short break. Is that right?
Yes.
And then.
10:40 again.
Okay, so we'll start at 10:40. Thank you.